Example 3D. Here is our latest system of equations that we are going to solve. Okay. All right. Let's set up our first matrix here. Okay. So just write down the numbers you see. Okay. So for the first equation, there's a 2 in front of x, 3 in front of y, 5 in front of z, 21 on the other side. Okay. Second equation, 1 in front of x, -1 in front of y, -5 in front of z, -2 on the other side of the equal sign. Last equation, 2 in front of x, 1 in front of y, -1 in front of z, 11 on the other side of the equal sign. Okay, so there's your initial matrix. Okay, now we start doing the Gauss-Jordan elimination. We are going to start in the first column. Okay, in the first column, we need to secure a 1 on the principal diagonal. Okay, we need this 2 to be a 1. Okay, so either you need to switch rows, okay, or if you can't get a 1 from switching rows, you need to divide this row by 2 in this case, because 2 divided by 2 would give you a 1. Okay, that would introduce fractions, unfortunately. But luckily, you see that you can switch rows 1 and 2 and get the 1 in this position. Okay, so that's what we're going to do there. Okay, so for the next matrix to get it, we are going to take row 1 and row 2 and switch those guys. Okay, all right, so let's go ahead and write down what we get. All right, so nothing's going to happen to row 3, so that will just stay the same. And then the current first row will now become the second row. And what was the second row will now be the first row. And now we have a 1 in that spot. Okay. All right. So continuing on, we need to zero out the rest of the column. We're still in column 1. Okay. All right. So now we need to put a 0 here. Okay. Gonna have to use the third row operation. Okay. So we need to take row 2 and add to it a multiple of a different row. Okay. What is going to cancel a 2? A -2. Okay. So since we are in the first column, we need to multiply the first row by something. Okay. We're going to multiply by -2 because that's what cancels +2. Okay. So if we do -2 times row 1, that will put a -2 in this position. And then you can add it back to +2 and get your 0. Okay. So for matrix number 3, to get it, the row operation is going to be -2 times the first row plus row 2. That's going to become the new row 2. Okay, so let's start writing down the new matrix. Okay, we're only making a change to row 2. So row 1 will stay put, as will row 3. Okay, let's go out to the side and do the work for the new row 2. Okay, so we're going to do -2 times row 1. Okay, again, write out your work. You're less likely to make a mistake. So we're going to get -2, +2, +10, +4. Go ahead and add the second row back to that. So go back to the previous matrix, get the second row. Okay, we add. Okay, -2 plus 2 is 0, 2 plus 3 is 5, 10 plus 5 is 15, 4 plus 21 is 25. Okay, so that is our new second row. All right, continuing on in the first column here. Okay, we need to zero out the rest of the column. So now we need to change this 2 to a 0. Okay, all right, we are still in the first row, first column. Okay, so that means we're going to have to multiply the first row by something. Okay, what's going to cancel a 2? Also a -2, just like the previous operation. Okay, so we are going to multiply the first row again by -2. That will put a -2 in this position. Add it back to the third row, you'll get your 0. Okay, so for matrix number 4, the row operation is going to be -2 times row 1. Add it back to the third row. That will become the new third row. Okay, all right, so let's write down our new matrix. Only row 3 is changing, so leave row 1 alone. And also leave row 2 alone. Okay, let's go out to the side and do our work. Okay, so we're going to do -2 times row 1. That's going to give us -2, +2, +10, +4. Add it back to row 3. Go to the previous matrix and get row 3. Okay, add. You're going to get 0, 3, 9, and 15. Okay, there's your new third row. Okay, all right, we are done with the first column. Okay, so now we can move on and start working in the second column. Okay, your first order of business is to secure the 1 on the principal diagonal. So this 5 needs to change to a 1. Okay, so the easiest way to do that, you don't want to switch rows here because it's going to undo your previous work. So we're going to have to do 5 divided by 5 is 1. Okay, so we're going to have to take the entire second row and divide by 5. Okay, so for my fifth matrix, okay, the row operation is going to be to take row 2 and divide it by 5, and that will become the new row 2. Okay, so let's go ahead and write this matrix down. Okay, row 1 will stay the same, as will row 3. Okay, now I'm just going to eyeball it here, and I'm going to take everything in the second row and divide by 5. 0 divided by 5 is 0. 5 divided by 5 is 1. 15 divided by 5 is 3. And then 25 divided by 5 is 5. Okay, so there's your new second row. Okay, continuing on, still working in the second column. Okay, now I need to zero out the rest of the column. All right, we're going to change this -1 to a 0. Okay, so again, you're going to have to use your third row operation here. Okay, so you're going to have to take row 1 and add to it a multiple of another row. Okay, since we are in column 2 now, row 2 is what we're going to want to multiply by. Okay, so you have a -1 here. Okay, what is going to cancel a -1? Well, a +1. Okay, so we're going to have to multiply row 2 by +1. Okay, that will put a +1 right here. Okay, add it back to the first row, -1. You'll get your 0. Okay, so let's go ahead, go to the next page and start writing this down. All right, to get my sixth matrix here, okay, the row operation is going to be 1 times row 2, and we're going to add that back to row 1, and that is going to give us the new row 1. Okay, all right, so only row 1 is changing. Okay, so I'm going to keep row 2 the same, and then I'm also going to keep row 3 the same. All right, and so then I'm going to go out to the side here and do my work. Okay, all right, so what I need to do here is I need to take 1 times row 2. Okay, so if you're multiplying anything by 1, it's basically staying the same. Okay, and then we need to go back and add row 1 to it. Okay, so if we go back and we look at our previous matrix and we look at row 1, it's going to be 1, -1, -5, -2. So 1, -1, -5, -2. Let me just make sure that's right before I write the wrong thing down. All right, and so now add. Okay, so this is going to be 1, 1 plus -1 is 0, 3 plus -5 is -2, 5 plus -2 is +3. Okay, so there is your new row 1. All right, so far so good. Okay, let's zero out the rest of this column. Okay, still in the second column. Okay, need to zero this guy out. Okay, got to change that 3 to a 0. Okay, got to use the third row operation. Okay, what's going to cancel a 3? A -3. Since we are in the second column, we need to multiply row 2 by something. We're going to multiply row 2 by the -3. Okay, you do -3 times 1, that will put a -3 right here. You add it back to the +3, you'll get your 0. Okay, so the next row operation is going to be -3 times row 2. Add it back to row 3. That'll become the new row 3. Okay, all right, let's start writing our matrix down. Okay, only row 3 is changing. Okay, so let's keep row 1 the same. Let's keep row 2 the same. Okay, go out to the side and do your work. We're going to do -3 times row 2. That's going to give us 0, -3, -9, -15. Okay, go back and add the third row to it. So go to the previous matrix and grab row 3. Okay, and now add. Okay, everything cancels. You get all zeros for row 3. Okay, so that's your updated matrix. So you're done with column number 2. So you should go on to column 3 and try to secure a 1 on the main diagonal. But we've encountered something like this before with the smaller systems, okay? Where you're trying to change one of these principal diagonal elements to a 1 and it's a 0. Really the only thing you can do is switch rows, but that undoes your previous work. So we concluded in the past that if this happens to you, there is no way you can get a 1 there, okay? So you're supposed to stop and interpret your solution, okay? So when you get here, okay, hopefully you realize that this last row is all zeros, okay? And remember, that is indicative of infinitely many solutions, okay? Why? If you took this row and translated it back into a system of equations, if you just translated this last row into an equation, you would get 0 times x plus 0 times y plus 0 times z is equal to 0, okay? And then if you simplified, you get 0 equals 0. That's a true statement. It makes sense. And so that is pointing to you that there are infinitely many solutions, okay? Again, I cannot emphasize enough, okay? Just like with this example, okay, if you cannot reach your goal, we could not reach our goal here, okay? Remember, what was our goal? The identity matrix to the left of the vertical line. If you cannot achieve your goal, that's either infinitely many solutions or it's no solution, okay? It is not exactly one solution, okay? Because if there were, you would get it, okay? Row of all zeros indicates infinitely many solutions, okay? You have to parameterize the solutions. Okay, remember, not every ordered triple is going to work here. Okay, you have to write down in a compact way which order triples work and which order triples don't. So you're just going to write down, well, actually the ones that do work. Okay, so let's talk about how you would parameterize the solutions here. Okay, all right, what we're going to do, this third row tells us that there are infinitely many solutions. To parameterize, we're going to rely on the other 2 rows. Okay, I'm going to start with this row. Okay, we are going to turn this guy into an equation. Okay, so we're going to have 1 times x plus 0 times y plus -2 times z is equal to 3. Okay, if you clean that up, you're going to get x minus 2z is equal to 3. Okay, I'm going to box that and I'll come back to that in just a second. Okay, similarly, I am going to translate this row into an equation. Okay, so let's see here. Let's do that. All right, so down here, I will translate this row. Okay, so this guy is telling us that 0 times x plus 1 times y plus 3 times z is equal to 5. Okay, clean that up. Okay, and we're going to get that y plus 3z is equal to 5. Okay, so all I've done, I took the matrix that I left off with and I translated the 2 non-zero rows back into equations. Okay, now it's time to parameterize. Remember, when you parameterize, you don't want to see x, y, and z. You want to see just a t, okay? One of the variables has to become t. The question is which one, okay? If you notice, look at these 2 equations we got left with. They both involve z, okay? They both involve z, okay? So what that tells us is that z is going to be the t, okay? Z is going to be the t, okay? Now, actually, let me move that because it's kind of in the way of my next step here. Okay, so z is going to become the t, okay? Now, to figure out the rest of the parameterization, we're going to take this equation and solve it for x. We're solving it for the variable that is not z, okay? So if you took this equation and you solved it for x. We're just going to add 2z to both sides. Okay, we're getting the x by itself. Okay, so x equals 2z plus 3. Okay, so this is what we're going to use going forward. Okay, and we're going to do the same thing to the second equation. Okay, z is going to be my t, so I'm going to solve for the other variable. I'm going to solve it for y. Okay, so we need to get y by itself, and we can do that by subtracting 3z from both sides. Whatever you do to one side, you got to do the other. Okay, so we're going to get y equals negative 3z plus 5. Okay, all right, so notice, okay, in doing this, you have two equations. You have, this is how you get x, this is how you get y, okay? X and y are both defined in terms of z, okay? So to write down your parameterization, now you can go ahead and do it, okay? Remember, you want to write down an order triple, x, y, and z. So x goes first, okay? Remember, we're calling z t, okay? So x is going to be 2t plus 3, okay? Y is going to be negative 3t plus 5. Don't forget the z because there's three variables. The z is the t, okay? This is your parameterization. This is the compact way of writing down all the solutions to the system, okay? In the directions, if it said if you encountered infinitely many solutions, you needed to parameterize and state at least one specific solution. Okay, so remember, if you want a specific solution, all you need to do is pick a value for t. T can be anything that you want, okay? T can be, you know, positive, negative, it could be a decimal, a fraction, okay? I always pick t equals 0 because 0 makes things go away, okay? So plug in that value, okay? So if we plug this into our order triple, so everywhere you see a t, put a 0, okay? Simplify, this is going to give us 3, 5, and 0. Okay, so this is one solution of the infinitely many to the system of equations. Okay, if your x value is 3, your y value is 5, and your z value is 0, that will work. Okay, and the great thing is you can check yourself. Let's see if 350 actually works. Okay, so go back to the original system here. Okay, and we can do a little check. So remember we said x is 3, y is 5, z is 0. That's one specific solution. Okay, so if you check this here, okay, look at equation 1. Okay, 2 times 3 plus 3 times 5 plus 5 times 0. Okay, if you simplify that, you get 6 plus 15, you get 21. Okay, so that works. Okay, if you look at equation number 2, okay, plug in these values. So you would get 3 minus 5 times 0. Okay, that's going to give you 3 minus 5, that's negative 2. That one works. And we'll get, let's see, we'll get for the third equation 2 times 3 plus y, which is 5, minus z, which is 0. That simplifies to be 6 plus 5, which is indeed 11. Okay, so this particular or specific solution does work. It checks out in all three equations. Okay, remember, this is not the only solution. Okay, there are infinitely many. Okay, all you have to do is pick another value for t, and that'll generate a different solution. Okay, so here was an example of infinitely many solutions. Okay, we're going to try one more system of equations with Gauss-Jordan elimination, and part E will be a little bit different because we're going to have the number of equations and variables are going to differ. Let's take a look at it.